AMB 26, why have you sent your attendance through chat box? I am actually telling you repeatedly. Every day I am telling these things. It is not required to send your attendance through chat box.
Sorry, ma'am.
I am calling the absent roll numbers. AMB 025, AMB 25. Just I am calling absent numbers, not this point. AMB 025. Civil Engineering 78, CB 078, CEB 078. CB 091, Civil Engineering 91, Civil Engineering 92, Civil Engineering 93, Civil Engineering 94. I repeat, CB 91, 92, 93, 94. Computer Science 59, Computer Science CSB 059, 59. Computer Science 63, Computer Science 63, 68, Computer Science 68, Computer Science 68. Electrical Engineering 55, Electrical Engineering 55.
Ma'am, Aerospace Engineering 025. Could you please mark me as present?
Okay,
Thank you, ma'am.
now I have given. Electronics 41, Electronics 41, Electrical 55, Electrical 55, okay, Electronics 41, Electronics 41, 42, Electronics 42, Electronics 42, Mechanical Engineering 49, Mechanical Engineering 49, Mechanical Engineering 49, Mechanical Engineering 52, 52, Mechanical Engineering 52, 53, 53, Mechanical Engineering 53, 54, 54, Metallurgy 30, 30, Metallurgy 30. Mining 25. Mining 25. Mining 25. Okay. I think I have called all the absent roll numbers.
Excuse me, ma'am.
Yes, tell me. Tell
Ma'am,
me.
ma'am, civil 81. Ma'am, have you mark me absent or present?
Civil engineering 81. You are present.
Yes, ma'am. Okay, ma'am.
Okay. I am marked. Okay. Okay. I am sharing the screen now. Actually, in the last class, just a minute. I have sent this class material to all of you. I have sent this course material to all of you, right?
Yes, ma'am.
Okay. Actually, the last part, I just recap the last part, this portion, just I recap, and then I will start the new topic today. You see, in this situation, where the differential equation is of this type, what is it? What is the difference between this type and the previous one? Yes, here in this differential equation, you observe that the order of the differential equation, and the degree of the variable are the same. Actually, this is a differential equation with variable coefficients. This is a differential equation with variable coefficients. Actually, here P1, P2, Pn minus 1, Pn, these are all constants, but the variables are present x to the power n, x to the power n minus 1, x, etc., etc. All these are variables. So it is a differential equation with variable coefficients. But this is a special type of differential equation where the coefficients are like this: order of the differential equation and the degree of the variable are the same. And this special type of differential equation is called Euler's homogeneous linear equation. And in this case, what will you do? We use some transformation like x equals t to the power t, that means t equals to log x. Then using this transformation, what happens? The differential equation with variable coefficients, which is specially called Euler's homogeneous linear equation, that will be transformed into a differential equation with variable coefficients. Actually, this is a differential equation with constant coefficients. That we have already observed. We use this transformation x equals to t to the power t, equals to e to the power t, and so t equals to log x, and so you see dx dt becomes x, and its reciprocal dt dx becomes 1 by x, and we have used this transformation here in this particular problem, where you see the order of the differential equation is 3, whereas the degree of the variable is 3. So it is a differential equation with variable coefficients, and also this is special type of differential equation which is called Euler's homogeneous linear equation. And so we have used the transition x equals t to the power t, that means t equals to log x, dt dx is 1 by x, but we are to calculate dy dx, dy dx2. Actually we have to obtain x dy dx, x squared dy dx2, and x cubed d3y dx3. All these are required. So we have computed dy dx, and so you see x dy dx becomes dy dt. Then we compute d2y dx2, and after simplification it becomes, you see, x squares d2y dx2 becomes this, which is actually theta square minus theta operating on y. Here actually theta stands for ddt. Capital D stands for ddx, already used this, but here we are to use another operator, say theta, which stands for ddt, but the different authors actually use different symbols for this operator, theta, delta, etc., d dashed. Any symbol may be used for this operator ddt. And you see x square d2y dx2 becomes this, theta square minus theta whole operating on y. And you see capital D stands for ddx, and so it is capital D square y. And this is actually theta, theta stands for ddt. So theta square means d2 dt2. So it is theta square y minus theta y. After simplification it becomes theta minus 1 into theta y. This is actually the value of this x squared d2y dx2. And finally we again differentiate this d3y dx, again differentiate this d2y dx2. You know d2y dx2 equals to this, d2y dx2 equals to this, and if we differentiate again to compute the third order derivative like this, d3y dx3, then ddx of d2y dx2, and after simplification it becomes x of d2y dx2 equals to this. Again you see theta stands for ddt, so it is actually theta cube y minus 3 theta square y plus 2 theta y, like this. And so just simplify this, just factorize this into linear factors, theta minus 2 into theta minus 1 into theta operating on y. So you observe this very carefully. This is x cube d cube y, that equals to this. There exists, if it is order of the derivative is 3, degree of the variable is 3, and on the right side you see there exist 3 factors starting from theta, theta minus 1, theta minus 2. You see, when you have computed x square d square y, that means the x square d2y dx2, then it is theta into theta minus 1 operating on y. There exist 2 factors. If the order of the derivative capital is 2, degree of the variable is 2, then there exist 2 factors, theta into theta minus 1 operating on y. When you have compute the first order derivative like this, you see x dy dx, that is actually x capital dy, which is actually theta y. There is only one factor. If the order of the derivative as well as the degree of the variable is 1, then the right side contains only one factor, theta. When it is x squared d square y, then the right side contains 2 factors starting from theta, theta minus 1. When we have computed x cube d cube y, there exist 3 factors, theta, theta minus 1, theta minus 2. So you just put these values when you are to compute x cube d cube y, then it should contain 3 factors like this starting from theta, theta minus 1, theta minus 2. So we put these values here to get the differential equation with constants, we have put these values here, and then after simplification, you see this is a differential equation with constant coefficients. You see, this is a differential equation with constant coefficients. And now you see the independent variable is t. Instead of x, now the independent variable becomes t. So you see, you are to use this y equals to e to the power mt. Instead of x, it should be written as t. Y equals t to the power m into t. This is the translation of the differential equation whose right side is 0. And you know, the auxiliary equation can be written very easily just by replacing theta by m. And then after computing the roots of the differential equation like this, here there is only one real root and another pair of complex conjugate roots. And you know how to write the complementary function in this case, which is this. And where you see we have used the ABC as arbitrary constants of integration, and we have computed particular integral. And you see all these have been done in the last class actually. And finally you see general solution is given by complementary function plus particular integral. Okay, and now we are to replace t by, you see, t equals to log x e to the power t equals to x. The original independent variable is x, so ultimately you have to convert the variables in terms of x, the original independent variable. So you should replace x e to the power t equals to x and t equals to log x like this, and finally we have obtained this solution. And another form we have discussed in the last class. Actually, it was discussed in the last class. I recap here today. Now you see here, you see differential equation same as the previous one, except here in the previous occasion you have observed this was x to the power n d, order of the derivative is n y, but here a plus bx. Each x is replaced by a plus bx. Just this is the difference. Each x is replaced by a to the power a plus bx like this. You see. Just you see here, you see, just you observe this differential equation. Compare this equation 1 with the differential equation. Now we are to discuss. You see here x to the power n, x to the power n minus 1 like this. Now you are to discuss another differential equation, which is a plus bx whole to the power n, a plus bx whole to the power n, nth order derivative dny, then p1 a plus bx whole to the power n minus 1, etc., etc. So you see each x in 1 is replaced by a plus bx. So the transformation should be like this. In the previous occasion we have used the transformation x equals to e to the power t. Now here in the differential equation x is replaced by a plus bx. So the transformation should be like this: a plus bx equals to e to the power t. Again you observe here order of the derivative is n, degree of the factor, linear factor a plus bx is n. Again you see order of the derivative is n minus 1 and degree of the factor a plus bx is n minus 1. So these two are the same. And in this occasion you are to use the transformation a plus bx equals to e to the power t. Now you use this transformation here. You see x is replaced by 5 plus 2x, 5 plus 2x, 5 plus 2x. So just we put 5 plus 2x equals to e to the power t. And then we use the same. They compute. Actually, we have to compute dy dx. Next, compute d2y dx2. Actually, we have to compute 5 plus 2x into dy dx. Next, compute 5 plus 2x whole square into d2y dx2. So that the differential equation, this differential equation will become a differential equation with constant coefficients. Here our purpose is just to transform this differential equation into with variable coefficients into a differential equation with constant coefficients. We use this transformation only to convert this differential equation with variable coefficients into a differential equation with constant coefficients. So just to use this transformation, and finally you see you have calculated this 5 plus 2x into dy dx equals to this. Again we use the same operator theta, theta stands for ddt. Then we have computed second order derivative of y with respect to x, and finally we have put these values here and obtained this. Again, you see, this is an important observation. When this is first order derivative and the degree of the factor 5 plus 2x is 1, there is only one factor theta. When we have computed 5 plus 2x whole square d2y dx2, then you see there exist two factors starting from theta, theta minus 1. Similarly, if you are to compute 5 plus 2x whole cube d3y dx3, then the factor on the right side should be theta, theta minus 1, theta minus 2. So here up to second order derivative, so there exist two factors, theta, theta minus 1 into 4. Again, the first order derivative 5 plus 2x into dy dx is this 2 theta y, and simplify this. Okay. Okay. And next you see our next, this is a differential equation, constant coefficients, no doubt about it. And you see right side is non-zero, so you have to compute complementary function and particular integral, same as before. You see we have computed, first we write down the auxiliary equation, find out the roots, then we find out complementary function using the formula. This is actually a pair of roots, but these roots are real and distinct. These are actually real and distinct roots, first case actually. So the complementary function should be like this, where here b are arbitrary constant, then we have computed particular integral, and finally we have written the general solution as this complementary function plus particular integral. And finally, you know, you have to replace t by x, that means e to the power t equals to 5 plus 2x. You have to use this transformation back to the pavilion, so you express the general solution in terms of x like this. Now we are to start the new topic. The new topic means actually new chapter. Now I will share different screen. I am sharing another screen now. Is it visible? Is it visible?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. Okay, today I will discuss another method which is called method of variation of parameters. Method of variation of parameters. We just use this method to solve this problem. We use this method of variation of parameters to solve this problem. You see, to solve this problem, we apply this method of variation of parameters to solve this differential equation. Actually, you see, this differential looks like the previous differential equations, like, right? You see, this is a differential equation with constant coefficients, because the constant coefficients are 1 and square. N is supposed constant here. But the right side, you see, sec nx. Do you know some formula for finding the particular integral where the right side function is sec or cosec? No. No formula is given to you to find the particular integral where the right side function capital X is sec or cosec. It is given to you when the right side function is exponential function or x to the power n type function, or sine x or cosine x, or e to the power x into v, or x to the power x into v, or x to the power n into v. These are the functions on the right side denoted by capital X when we have computed the particular integral. Actually, you can apply this method of variation of parameters. Whatever be the function on the right side, you may apply this method of variation of parameters. It is not for only sake cosec like this. Okay, what is this? The method I am telling you the steps, this method step by step. First of all, you see the differential equation is given by this. You first observe what is the solution of the differential equation whose right side is 0. We consider the same differential equation whose right side is 0. That means just we take this equals to 0. Okay. And you see, if we solve this differential equation with right side 0, then that solution is called complementary function. Already it is known to all of you that we first solve the differential equation whose right side is 0, and after solving this equation we can write down the complementary function. So we can write down the complementary function here by putting 0 on the right side. Left side remains the same, and we write down the complementary function, which is actually y equals to c1 cos nx plus c2 sin nx. This is the complementary function. Now this is the starting point of this method of variation of parameters. Just we assume here c1 and c2 are not constants. In the previous occasions when we have computed complementary function and particular integral, in that case you see we have considered c1 c2 as constants of integration, but here these are some parameters containing the variables. In this particular method we considered c1 and c2 are not constants, these are functions of x. This is the starting point of this method of variation of parameters, where these coefficients a and b are functions of x. Note this point, I just tell you that this is actually, idea is this, we have computed the complementary function where the coefficients c1 c2, say capital A and B, which are functions of x. Now you see you have to compute, you see you have to compute actually d2y dx2. Okay, so we first compute dy dx. We first compute dy dx. You see, most important thing here, a and b, these are functions of x, and also you see these are unknown. We have to compute the values of a and b. Somehow we are to compute the values of these coefficients a and which are actually parameters which are functions of x, and we have to compute the values of a and b. So since there exist two unknowns, so we are to require two equations containing two unknowns. We are to somehow form two equations containing two unknown parameters a and b. You first compute the first order derivative. You have to compute dy dx, and when you have to compute first order derivative, actually we have to compute second order derivative, because you see the differential equation contains second order derivative. We have assumed y equals to this a cos nx plus b sin nx, and then you have to compute d2y dx2, and then you have to put these values here. So we first compute first order derivative, and since a and b are not constants, they are functions of x, so this will be considered the product of two functions of x. Again, b into sin x will be considered the product of two functions of x. So you see the dy dx should be a into derivative of cos nx, that is minus n sin nx, plus cos nx remains unchanged, dA dx, that is a will be differentiated with respect to x. Similarly, b sin nx, product of two functions, you differentiate sin nx, which is in cos nx, where b remains unchanged. After that, b will be differentiated with 2x, that is dv dx into sin nx, like this. And here actually we use this symbols e1, which is actually dA dx, and b1, which is actually dv dx. Now we are to choose capital A and capital B such that this equals to 0. We choose A and choose A and B such that this part becomes 0, like this. This part becomes 0. And when we choose A and B such that this equals to 0, that means if we use 3 here, then what will you get? dy dx equals to minus a n sin n x plus b n cos n x. Because by your assumption, this equals to 0. And so this equation becomes dy dx equals to minus a n sin n x plus b n cos n x. Now you have observed that the differential equation what we have to solve now contains this d2i dx2. So second order derivative should be computed. We have computed only dy dx, and you see you choose A and B so that this equals to 0, and finally if we put this equals to 0, then dy dx equals to minus a n sin n x plus b n cos n x. So we have obtained this. Again we have to differentiate to compute d2i dx2, and again we have to compute d2i dx2, and again AB, note this point repeatedly, I am telling you A and B are not constants here, they are functions of x. So A and B must be differentiated with respect to x. That means A into sin nx should be considered as product of two functions of x. Again B into cos nx should be considered as product of two functions of x. And so if we differentiate d2i dx2, then again you see sin nx should be differentiated, which is n cos nx, where a remains unchanged, and next a will be differentiated with respect to x, that is d a dx. D a dx is written as a1 here, but n sin nx remains unchanged, and makes a will be differentiated with respect to x, that is d2i dx. So after this differentiation, it will become d2i dx2 equals to this. And you see a cos nx plus b sin nx is actually using the original differential equation 1. Okay, this is actually, just a minute, a cos nx plus b sin nx, which is actually y. You see here, yes, y equals to this, a cos nx plus b sin nx. So it is y actually. A cos nx plus b sin nx is y. And this other terms remain unchanged. And so we just put the values of d2i dx2 and dy dx is in the original equation 1. We put the values of d2i dx2 and y in 1. Then what we get? You see, just we put the values in 1 and obtain this. You see, minus e1 in sin nx plus b1 in cos nx equals to sec nx. This is actually number 4. And number 3, so we have obtained two equations, 3 and 4, containing two unknowns a1 and b1. Where you see a1 means d a dx, and you know b1 means db dx. So we have obtained two equations 3 and 4 containing two unknowns a1 and b1. Where you see a1 means d a dx, b1 means db dx. So we have obtained two equations, namely 3 and 4, containing two unknowns a1 and b1. So we can solve 3 and 4 for a1 and b1. Suppose if we eliminate a1, then you can solve for b1. How to eliminate a1? Just you apply method of elimination. So you see this is a1 into cos nx, but here a1 into sin nx. So you should multiply equation 3 by n sin nx, n sin nx. You see multiplying 3 by n sin nx, and equation 4 will be multiplied by cos nx only, and then we adding the results thus obtained, then we will get this b1n equals to 1. So b1 equals to 1 by n. Just actually you have to solve equations 3 and 4 for a1 and b1. Just we solve equations 3 and 4 for a1 and b1. You can eliminate b1 first, then you will obtain a1, or you can eliminate a1 first, then you can obtain b1. b1 equals to this. And then from 3, you see, by putting the value of b1, you can obtain a1. a1 equals to this. But you know, you have to calculate a and b. So a1 should be integrated because a1 means da dx, and you know b1 means db dx. So db dx is known. So b can be computed just by integrating both sides. a1 equals to this. So in order to compute a, you just integrate a1 with respect to x, and b with respect to y. and then you say tan nx, whose integral is sec nx, but here it is minus 1. So minus 1 sec nx power minus 1 is actually log of sec nx. Now it is this minus sign is absorbed, so it is log of cos nx. And now it is C1 as the constant of integration. We have computed A means A1 means dA dx. So in order to compute A, it should be integrated with respect to x. So A becomes this. Just integrate both sides to calculate A. And B equals to, you see B1 equals to 1 by n. So B means integral of 1 by n. Okay, so it is this x by n. B1 means actually, you see, the value of B1 is 1 by n. So it is 1 by n, and integral dx means x. So x by n plus C2. Okay, we have computed B, and here we have computed A, and so we put the value of A and B and obtain the solution like this. Here we did not compute particular integral, just we have computed complementary function for to write down the solution. You see, we have just computed the complementary function, and then we have assumed this solution in this form, where only difference is this. In the previous occasion C1 C2 were constant, but here A and B will be considered as functions of x. These are functions of x. And next we have computed dy dx, dy dx, etc., etc. And finally, you see, in the intermediate steps we have used this. You see, d2y dx equals to this. Okay, you see, dy dx equals to this, and now we choose, actually here a1 means dA dx, b1 means dB dx. Okay, and here we choose, actually here a1 means dA dx, b1 means dB dx. Okay, and here we choose a and b such that this portion equals to 0, and after that dy dx becomes minus an sin nx plus bn cos nx. If we choose a1 cos nx plus b1 sin x, nx equals to 0, then dy dx becomes this minus n sin nx plus, you see, bn cos nx. After that we have to compute d2y dx2, because in the original differential equation there was d2y dx2, so we have to compute d2y dx2. Okay, and then we simplify this and obtain this. This is the method which is called method of variation of parameters. Okay, after that you have obtained two equations 3 and 4 containing two unknowns a1 and b1, solve 3 and 4 to obtain a1 and b1, and when we have computed a1 and b1, we integrate them with respect to x to compute a and b respectively, and then we put the values of the variables a and b in this case y equals to a cos nx plus b sin nx, where a equals to 1 by n square log cos nx plus c1, and b equals to this x by n plus c2, like this. A means this, b means this, and then simplify this and obtain this. This is the method which is called method of variation of parameters. Okay, now stop here. Now stop sharing, stop presenting. Okay, may I leave now? Method of variation of parameters, is it clear to all of you?
Ma'am, I have a question, ma'am.
Yes, tell
Hello.
me.
Madam, what is the syllabus
Yes,
of
yes.
this semester exam?
Actually, that will be decided today or tomorrow in a meeting. The meeting today, we have a meeting in the evening. After that, I can tell you.
Okay, ma'am.
Okay.
Hmm.
Today we have a meeting where it will be decided the syllabus exam. And after that, I will try to connect your CR, and then I can tell you. Okay. Through CR, I think it will be known to all of you. Is it clear?
Yes, ma'am.
Is it clear?
Yes, ma'am.
Okay. May I leave now? May I leave now?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Okay, I leave.